Okay, this is a video about what it means to be a function. So we have things called relations, and relations are any set of ordered pairs. So you can list them. It doesn't matter what they are. Whatever is in the first elements, I guess I'll put one more. These are called the domain. And whatever's in the second spot is called the range. So this typically falls under what we would call the x's are the domains and the y is the range, typically. So a relation can be anything that relates to sets to each other. So you could take a domain over here and a range over here. And if you go like that, that means that you have the ordered pair 1A. 1 goes to A, maybe 2 goes to C, and maybe 3 does too. Pretend there's a bracket over there. So this is a relation. I could also put 2 to B, and it would still be a relation. So the thing that makes a relation different from a function is, so here's the domain, here's the range, and when you're doing a relation, basically imagine that you're actually shooting arrows. So if I put 1A and I draw an arrow, that means I have the ordered pair 1A. But in your mind, imagine that 1 actually shot an arrow. So in a relation, 1 can have all the arrows that it wants. But in a function, let's pretend that this is like a competition and everybody only gets 1 shot. So if I had 2 arrows coming from 1, so I also had 1B, then 1 cheated. It shot 2 arrows, and that's bad. So because 1 appeared 2 times in the ordered pair, that means it shot twice. So it's not a function. But if I don't have that, and everybody only gets 1 arrow, then it's a function. So 2 can also go to A. This is okay because this is like Robin Hood, right? So the arrow got split, but that's fine. Nobody cheated. So 2A is also here. The y's repeated, the x isn't, so it's fine. 3C, 4B. And that's a function. It's a function because everybody only shot 1 arrow. So if you have a visual like this, you can just check for any time there are 2 from the same spot. If you have a list like this, you just check the x's and make sure that none of them repeat. Okay, so what if you have something like, if I have this and I want to know, is y a function of x? So this notation means function of a variable. Okay, so it's a statement that it is a function. So you can't use this notation on something which is not a function. We can't just replace y here with f of x. But you try to solve for y. And if y ends up being something which, when you plug in a given x, you always get the same value, then it's a function. So the first step is solve for y. So I end up with y equals negative 12/7 plus 4/7 x squared. So if I plug in an x, there's only one result that can happen. Whatever that x is, when I square it, we'll always get the same thing, and then you multiply by 4/7, you always get the same thing. Subtract 12/7, you always get the same thing, so this is a function. So the way it gets to be not a function is if you have, say, y squared plus x equals 9, you try to solve for y. And right here, when I take this root, if I just had this, that's fine. That's a function. Pick your favorite x that doesn't make this negative, so it's bigger than or less than or equal to 9. And then you'll get a value, and we'll always get the same value. But when I take the root here, I have to say plus or minus. Because if y is 2, this is 4, but if y is negative 2, this is also 4. So I have to do a plus or minus here. So this is not a function because you can get two different values. If I choose x equal 5, and I plug it in, and I get plus root 4 is 2, minus root 4 is negative 2, which one's right? We don't know, so this isn't a function. Because we have 2, 5, negative 2, 5. Both of these work here. This, if you have a graph, basically if every x only gets one y, then every fiber can only cross at most once. So if you can do anything you want like that, as long as every vertical line only crosses one time. So if I had the thing I had before where x squared plus y squared was, or no, I guess that's not what I used, but the one I had before, the y squared, and there was an x and there was a 9. So it would have been either like this or opposite, because I don't remember exactly what I put. Pretend that kind of looks quadratic sideways. So the vertical lines pass twice everywhere, but here they pass once, and then over here they never pass, which is fine. It can have a restricted domain. But because this x gets this y and this y, that's why it's not a function. So that's called the vertical line test. I think also in this section is increasing, decreasing, and constant. So everything is left to right. So if you have something like this, you feel like that's increasing because you can't start at negative infinity, so you start somewhere that you can see and then it goes up. But from left to right, this is going down. So this is decreasing to here and increasing thereafter. Increasing, decreasing, and constant depends on the y's, but the location is always given by x. So let me make one that's a little more interesting. So let's say that we go like this kind of quadratic situation to here, and then pretend that's a horizontal line I just drew. Say to there, and then like that. So it was increasing to here because it's going up, 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 up. So increasing from negative infinity to negative 3. It's constant from negative 3 to positive 3. And it's decreasing from here on. Let's suppose that this turned around again at 10 and started going up. Then this would of course be 10. The increasing would say union 10 to infinity because it's two different places it's increasing. You just put a union in between. Now let's assume that you're given like then if you're asked to evaluate, say f of 3, x is in the parentheses, now 3 is in the parentheses, so x was our label. X is just a placeholder. So we're saying f of a thing equals the thing squared minus the thing plus 2. So we put the thing and square it minus the thing plus 2. Now, suppose instead of being given a number that you were given something with a variable still in it, which I think probably you're not at this stage, but might as well touch on that while we're here. Let's suppose this said a minus 2. This is still a placeholder in all places, so I take the thing squared minus the thing plus 2. So then we would distribute out so that we can combine like terms. So I distributed the negative also. So I have a squared minus 4a minus a plus 4 plus 2 plus 2. And that about wraps up functions.